So I've covered FFT right so far. Now we are going to use FFT to solve PDEs. Okay? That's one of the things we want to do in the course. So we use FFT to solve differential equations. Okay, PDEs. All right. So the idea is quite simple. Again, I've taken this from my book. So this is a PDE. So phi is function of x and t. So in the left hand side, d phi by dt, and the right hand side is f of some function, which is function of phi, partial x, second derivative, or it could be third derivative as well. Okay, we are doing 1D right now, and time. Okay, so this is some complex function. For example, Schrodinger equation is grad square phi. In 1D it is like that, plus v psi, right? So minus of this. So the v, in fact, okay, v is some function of x. Okay, so I didn't write it here, but there could be some function of x as well. Okay, so it's some function of phi and its derivative and some x and t. Now what we do is we perform Fourier transform of this equation. Okay, so what do I mean by that? I just multiplied both sides by e to the power I kx and sum over all x. Okay, it's a discrete, so x will be discretized, but when I sum over all x from both sides, the left hand side becomes, well, I mean, the sum and d by dt commutes, right? So sum of phi of x e to the power I kx sum over all x is phi k, phi hat k, this one, this object. Okay, the right hand side, if I do this, f is some function. Its Fourier transform is f hat k. Okay, so okay, now there is a okay, so that's what we will get for every, so for this 1k. Now we can do it for all k's, all wave numbers of the box, and this is general equation. Of course, the k can be allowable, whatever k is allowed for that box. I hope this is clear. Okay, so this standard thing which I did in my computational physics course, and I'm sure you've done it elsewhere as well. Okay, now, so k will, so suppose I make a discrete box 0 to n minus 1 in 1D. So wave numbers, if it is if psi is complex, this phi is complex, then number of wave numbers will also be 0 to n minus 1. So this will be k. Okay, so we'll have n minus 1 equations. So the number of equations for complex to complex when phi is complex is n minus n equations, 0 to n minus 1. Okay, so we have n ODEs, ordinary differential equation. This is ODE. This phi k is function of time. I've frozen k. Now it turns out k is discrete in most of the numerical work, because I take a periodic box, I've discretized it, so k will be, as soon as you take a periodic box of size L, then k becomes discrete. K is continuous only when box is infinite. Okay, and in simulations, we most often we don't use infinite box. Okay, it's always finite box. Now I hope I'm not sounding Greek. I mean, this is what is the spectral method. Now this ODE solver, you can use any method, Euler, RK2, RK4, Adam-Bashforth. You can solve this. Given initial condition, I can solve phi at any time. So idea would be, I will be given phi x. So from this I get phi k at k at t equal to 0. So this is known. And now this phi hat k will be time advanced. This is t equal to 0. I can go up to phi hat of k at t final. So I do dt, 2 dt, and so on. Okay, so this is how we solve a PDE using spectral method. Of course, the problem is how to compute this right hand side. Okay, that could be the issue. I'm going to come to that in a while. So let's take a concrete example. So Burger's equation. So this is a PDE. So this and this, well, this is a partial derivative in u, partial u, partial t, and this will be the basically f if I take this to the right hand side. Okay. Now we can rewrite the nonlinear term as this, no? So you can go inside like that. So if I convert it to Fourier space, so this I take it to right hand side. So this term has become that. Now this term I write like this. So d by dx will give you minus ik. There's a minus sign. No, it goes to right hand side. So minus will come because I push it to the right hand side. Okay, minus sign. Then derivative will give ik. Now I'm sure everybody should know that. Okay, each derivative brings an ik. Now Fourier transform of u squared by 2 is this u squared Fourier transform by 2. So I'm not writing this as a convolution. Typically u squared Fourier transform, in fact not typically, mathematically at a wave number k is up uk minus p, sum over all p's. Okay, this is an expensive operation. Why? Because for every k I have to do n multiplication and sum as well, and there are n k's, so this is order n squared. Okay, so this operation is expensive if I do using convolution. What we'll do is we'll compute this using Fourier transform, and we can do this in order n log n. Okay, so that's the beauty of FFT. So it can provide you convolution in order n log n. People in electrical engineering would know this very well. So convolution, you do it using FFT. Now this term new grad square u or new second derivative of u with x is this, right? Because this ik and ik twice gives you minus k squared, and that's what it is. So the nonlinear term I denote it by n hat k, and I'll show you how to do it using FFT. Okay, this one. Okay, so quickly. So at any time step when we start it, we are given Fourier mode UK. Okay, at any step, since I'm Fourier space, I have u hat k for all k's. So I perform inverse Fourier transform, I get to ux, right? Inverse Fourier transform. Then I multiply with itself, then I get u squared, right? So this one is order n log n. And it gives you for all k's. No? So for I will get ux at every point in n log n. This is multiplication at each point, so it's order n. Then after that, I perform forward FFT. So that gives me u squared hat k. So this is what I want, and this is n log n. Now after I got this, remember I need ik by 2. This one is coming in front. Okay, so I just multiply by ik. Okay, ik by 2, I should say ik by 2. And I will get this. And this is order n. So overall, I have 2n log n. Well, this order means I don't care about prefactors. So this whole operation is order n log n plus order n, but this is weaker than n log n. So the overall operation for computing the nonlinear term using FFT is order n log n. It is not order n squared. Okay. So that's the trick. Now there is only one catch, that this problem called aliasing. I cannot discuss it right now. People who are doing the project, they'll have to worry about it. So it turns out, if I have so let's say I imagine that I am doing this f hat k sine kx. Okay, I'm just doing for sine. Okay, so last wave number will be sine of nx. Okay, there will be 2 pi. Well, let's just do sine nx. Okay, there will be factor 2 pi and so on. Now, when I do the square, I'll get sine square of nx. Correct? So sine square of nx, when I convert it to, it's a quadratic, we convert it to linear, it's going to be cos 2nx by 2. Right? I mean, there is the expansion. So when I square it, I'll get one term will be sine square nx. So when I do the simplification, I'll get 1 minus cos 2nx by nx. So this corresponds to wave number 2n, which is not there in my box. This wave number is outside the range. If it's outside the range, what will computer do? Now, if you look at the theory of Fourier transform, it turns out this is going to be coming back. Okay, now people who have done something of FFT, Fourier transform, theory of Fourier transform, suppose my real spectrum is like this, maybe like this, going down. But my wave, my cutoff is here, my maximum wave number is here, this k, wave number k, okay? This spectrum, mod uk squared. Then what happens to these ones? It turns out it gets reflected and gets added up into that. Okay, so if I don't resolve properly, if I choose less n than what there is, I mean, that means my grid is less than the maximum wave number, then you add them and the what will come in the FFT will be this. Okay, if you've done any Fourier transform in project or something, you'll find that at the highest wave number, things just go up like that. And sometimes if there's just too much of energy here, then it just grows like that. So this may as sometimes it just becomes like that. Okay, like that. So this is called aliasing error. Okay, so this is the aliasing error. Alias means for a given wave number k, there are two guys who are contributing. One is the original man, other one is some alias, somebody else with coming at the same name. Okay, this is called aliasing error. I don't have time right now. This is HPC course, it's not a course on FFT, so or Fourier transform. So we will not discuss it. People working on the project on FFT, we can discuss it separately. Okay. Now this was Burgers. The fluid is pretty similar. It's just that there are more variables. Okay. So let's say we are incompressible flows. Then this is called Navier-Stokes equation, which I discussed while doing finite difference. Pressure, velocity field, some external force, and this is the constraint, incompressibility constraint, del dot U is 0. Okay, compressible equation, that constraint del dot U is not there, but we have continuity equation, this one. We have momentum equation here like that. There's one new term, del dot U is sitting there, and there's one equation for connecting pressure, the sigma, with pressure density. It's called equation of state. Okay, so we need to solve for rho as well as u. Sigma is solved by this. Okay, so you have to solve for, in 3D we'll have 4 variables. In incompressible flows there are only 3, ux, ui, uz. Density is constant. Now idea is pretty simple even for this one. Let's look at only momentum equation, velocity field. Okay, so this is coming from the u dot grad u term. Okay, I'm assuming incompressibility right now. Okay, so u dot grad u is written as del j uj ui. Okay, now I hope you know this notation. J is repeating index, so it means summing up over all j's. Okay, which we don't write it when it's repeating. So in fact, sorry, this m here. Okay, now when I do the Fourier transform, I'll get minus I km. Now I used j for minus of square root minus 1. Okay. Sometimes people use j for square root of minus 1. That's why I use something else for instead of j, I'm using m. So this is basically this nonlinear term. And now this is the Fourier transform of product ui and minus I. This is square root of minus 1 ki pk and that. Okay. Now this term is computed exactly like what we did for Burgers. If I use convolution, it will be very, very expensive. So we do using you compute this using fast Fourier transform. So we have the Fourier mode, inverse Fourier transform, real space, then multiply, this with some other. So we have velocity field, no? So one component with other component. So we have 9 of them, but because of symmetry, there are only 6. So you'll have something like UX, 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 UI, UX, UZ. So there are 6 combinations. And that is sitting here. Perform fast Fourier transform of this, so I'll get that, and multiply by this this stuff. Okay, IKL. I mixed up I with J. So this is square root of -1 in front. Okay, so this is the trick to compute the nonlinear term, and it's all done. I mean, we do this all the time. So our spectral code, this is written in C++. It was tested when we tested for FFT. We also tested for our spectral code, and this is for same grid, 768 something, 1500, and 3000. Okay, appropriate number, and 3000 is there's some numbers. So these are the scaling. T inverse versus processor. This is in log scale is linear. Okay. Now we can do a weak scaling by P by n cube, 768 cube. Okay, so they are collapsed into single curve. That means it is also satisfying the weak scaling. There's one, I mean, this 1500, well, things taper off. This is a tapering off. Here, this is a problem point. But other than few points, they're roughly linear. Not linear. I mean, log scale is linear. Okay, so this code is going all the way up to 200,000 processors. This is 200,000. Okay, so projects using spectral method, pretty much similar things. Burger's equation, compressible Navier-Stokes. We will not solve incompressible, okay, because that requires, we have the code, and well, some people may do it, but I'm right now proposing compressible. Well, I've written incompressible. So anyway, we will allow this as well. Schrodinger equation and Gross-Peterwitsky equation. There's nonlinear Schrodinger equation. And you need to parallelize it using MPI. Well, forget about this one. NVIDIA hardware. So basically, make it run on GPU and OpenMP. So objects in Python. Okay, so well, object-oriented programming is buzzword now. We can do it in, well, most modern languages give you this feature. C, C++, Java, all of them have objects. Okay, Julia, they have objects. So I taken my material from some of these references. You'll find this, well, I mean, I'm going to share this PPT with you, so you'll find it. These are simpler ones, and this is more technical. This is really, I mean, it's a python.org, so this is somewhat technical. Okay, anyway, so I'll give a brief summary. I'm not going to go deep into Python objects. I'll introduce things with which you can write your code in object-oriented fashion, your code for the project. Okay, you're not going to become a master of object-oriented programming by listening to this one lecture, but you can do it. I mean, you can do the projects with that, and you can also write simple ones. You'll have working knowledge after this lecture, and if you do something, okay, I mean, this lecture is not enough. You need to kind of grasp it. Okay, why object? So normally, well, all languages, Fortran, C, they provide data structures. Like array is a data structure. Okay, integer is one character, or integer is also a data structure. It's called integer data structure. Okay, so primitive data structures are provided by standard languages. Okay, of course, you can make more complex data structure, which C allows. We can, within some structure, we can put in different types of elements. Okay, so complex data structure can also be constructed, but that is not object-oriented programming. That's an object, but it has only data structure. So what we want is associated functions along with the structure. there could be some functions associated with it, so that whole thing becomes a black box which can be used by somebody else without getting into inside the box. So I'm going to illustrate by some examples. So you'll see that I'm going to use complex numbers as an example. So somebody gives you a complex number, but doesn't give you the function for multiplying complex numbers. Then you have to write yourself that it's not the full abstraction. I need functions associated with the data structure. Okay, so that is the associated function. So classes, so this class, so you'll hear the word class. So class is definition of this object, which has data definition as well as function definition. So classes enable building data and associated functions together. So that's the beauty of it. So we can also write functions associated with the object, and it helps in abstraction. So you can abstract. Abstract means so this is a very common word used all the time. Okay, let me just get the chat box open, or you can also unmute because it's just one-way traffic is kind of boring as well. So what do you mean by abstract? Can somebody tell me what is abstract? Mute and unmute and tell me what is abstract. But somebody should speak up. Okay, I mean, you heard this word abstract, no?
So basically, sir, it means you don't need to know the underlying design or implementation, how something is implemented. You just need to know what function it performs.
Okay, somebody else? Stripping away nitty-gritty details of something. Okay. Okay.
So it is getting the relevant data and hiding the irrelevant data.
Okay. Yeah, it's correct. I mean, but this is computer science. But what about abstract thing in elsewhere? Can you give an example? Good. This
So
word
basically in maths, basically if you set and a vector space, those vectors can be functions or anything which follows those axioms, and those are basically abstract objects, and anything which follows those axioms will satisfy the properties of vector space and all the theorems of vector space.
But that is different than what you are doing it here. No, you are that is not. I mean, but this abstraction of in coding where you are treating like a black box, you are not worrying about the details, is different than mathematics data abstraction. Is that correct?
Yes, sir.
Or is it same? Or in some sense, it is same. No, good
Yeah,
attempt. I mean, it's good. Is answer, but try to see the connection. What is the connection? Anyways, good. So there's Hamiltonian formalism for representing physical problems. Hamiltonian formalism. Okay, what about quantum formalism? Is it abstract or no? Is quantum formalism abstract, Narwar? Okay, so of course, I mean, there are different ways to, well, I mean, abstraction, let me just tell you my perspective. So you heard of coffee abstract, no? Right? Coffee abstract or coffee abstract is used of, or in chemistry, there is something called abstract, right? I mean, you might have heard this powder is abstract. And you can put that powder in a solution and it will give that manifested chemical. Am I correct? There may be some chemistry inside in the world, and in philosophy, the uses what is used as abstraction is in fact even in religion. So there are this world is a manifestation of some abstract principles or abstract things. So using basic material or basic formulas, this whole world has appeared. Okay, so abstract may not be visible or you cannot see it. but it is something inside which is creating all this visible world. So that way the Hamiltonian formalism, or so these are abstract formalism. So Schrodinger equation is an abstract formalism. Okay, when I see electron, it is not very Schrodinger equation. We don't say that. So it is well, I mean, it's a slightly far-fetching thing, but there are certain underlying principles or designs which are giving this manifestation. The way the chemicals, so chemical abstract, if you put in solution, then it will manifest itself as something which is usable or drinkable or whatever. So similarly, in computer science, we have a big code, but there are certain math functions which are already coded. So we don't need to worry about what is there in that math function. We can simply use that as a black box. So when I write this big algorithm, so I write this thinking at a higher level. So it is in fact multi-skill thinking. Program design is multi-skill thinking. So I want to solve a big problem, then I write pieces. So let's say spectral solver. So say, well, I'll have FFT, then I'll have a derivative calculators, non-linear calculators, and then input-output. So these are the pieces. And then each piece will have more functions and more things to do. So these called abstract design. We don't have the code yet, but we are putting the pieces together. And then finally we'll start coding when each box will get a C code or Python code inside the box. Okay, so the algorithm is in some sense is abstract design of the code. Okay, it's a formula. So that is a reasonable, I guess. Am I correct in this? I mean, people agree with me? Now, these are, of course, very qualitative way to say things. We can write a book on it, but anyway, this is how we can think about it. So, but it's important. You can't simply code 1 lakh lines of, a code of size 1 lakh lines or 15 lakh lines. We need to have this boxes in which the code, well, box within box within box, and then codes will go in each boxes, and you put them together, and that will be the big code. And when we're assembling those boxes, it is very important to have separation of the tasks. Imagine that if you're some data which is a global variable. Now I used a global variable and I tinkered it in one function, which other function did not expect that tinkering, and then the whole thing will collapse. So that's one of the reasons why people say do not use global variables, because each guy should be working independently, each function. And global variable means I just relied on somebody else not making a mistake or changing things. Okay, a global variable is a dangerous thing, right? So it spoils this clean separation of objects. Okay, and if you have functions, I mean, imagine if you don't have objects, then we cannot define functions separately for each object. Okay, so I will illustrate it. So it's a good idea to make the full thing, function plus data, in a package. And then outside guy doesn't need to worry about it. Well, what is there inside? Of course, you have to tell them what are the functions available and what are the data available, but then that person can use those functions for the data. Okay, so that's the beauty of this object. So we can make independent objects and build them more complex object using its constituents. So when architect, is designing a complex building, think of floors, corridors, entrance, and so on. Okay, so that person is thinking of objects, not bricks and mortar. Okay, so you can't build a big building with thinking of bricks. So in physics, no, people may. So I am against this reductionist approach, that you can derive everything once you understand the basic principles. Okay, there's a big paradigm. No, I mean, people say, well, if I understand particle physics or something, then I understand the whole world. Because it turns out that we do design at a different level and there are laws at different levels. So that's a philosophical aspect. Anyway, so we don't have time, or this is not the class for it, but it's an interesting observation. So class definition. Okay, so Python class. So we have class definition. It's a generalization of function definitions. So function definition, we have def, function f, and we give arguments, and colon, then we define. In class also, I'll show you the syntax. So basically, class is a definition, and you create an object by instantiating a class. So these are very different things. When I define a class, doesn't mean that class, I have an object. Object will be created after the definition. Okay, this is a very critical observation. So class instantiation creates an object with the data and the properties of the class. Okay, so you define it first, then you create objects of that particular class. So in Python, the function is called init function. Okay, so this will create the instantiate inside the class. So I'm going to illustrate it. I'm just going to show you, but I'm just describing some of these things beforehand. A method is the function associated within the in the class. Well, it should not with the class objects actually. Okay. And you can delete a class, delete an object, or you can also delete a class definition. Yes, you can delete a class definition. Okay. So let's see one example. So I said complex number, no? So we take I want to define complex numbers. So I have to define the data as well as associated functions. So the keyword is class. Okay, this is a class. Instead of def, we have class. Define function, def. So class, name of the class. So complex. I put a class, put a colon. Then this initialization. Okay. So remember, I mean, in Python, we don't declare the variables. Okay, int, float, all that is not required. We straight away get into initialization. So I have the real part and imaginary part of that object. Okay, so the object, right now I have not created the object, right? I mean, okay, so you give me 1 minute. So given this complex, I will create object in the next slide, but it's created like this. So I say A equal to complex, and inside this you give the arguments. So it takes two things, real number, real part and imaginary part. So let's say 1, 2. So this will be 1 plus 2j. Okay, so that's what. So this is the imaginary part, 2, and 1 is thing. So this is how we create object A of class complex. A is the object which is created. Okay, and it has two components, two data inside. One is the real part, which is R, and imaginary part. But right now A is not there. I mean, when I define this function, there's no name of it, right? I mean, the data is not yet, the object is not yet created. So we say, well, call it self. Self is the name of this, okay, self. So self.r, that means when I call this, I would have said a.r is 1, in fact. Okay, that will give us 1. It's a print a.r, a.r. Dot is go within. Dot is like a room within a building. Okay, so you're going inside. So self.r is object, the real part. Self.r is a real part. So real part is the argument. Okay, so the real part 1 is the argument. Imaginary part is an argument. When I instantiate it or start it, so these are the arguments are passed here. So this will be the first function. When I instantiate it, this function is executed and it is associated with init. I hope this part is clear. When I create an object with some argument, it's just going to look for init function and match the arguments. Okay. So the real part and the imaginary part are the arguments, and that is assigned to the real part of the self and the imaginary part of the self. So I just use a shorthand notation R and I. Is that clear? People can ask me a question right now. Okay, so let's go to the next thing. Now I have defined 3 functions associated with the class. Print. So print the number. So I give the argument, okay, self. Well, itself is giving the thing. So print self.r plus self.ij. So this will be basically the output, 1 plus 2j, right? So these are plus are characters and j is a character. Okay. So this is a one of the functions associated with the object class of the class, actually. Let not say. So once I create the object, I'll say a dot print number. When I with a bracket, self means you don't give anything. Okay, self means I should not write self when I call it. Here I should not write self here. Okay, self is a dummy argument. So let's add. So I add x to self and update it. Okay, so this is going to update the value of self with x. So the real part of self will be updated with x dot r. I mean, plus equal to means added. You know, this added. And the imaginary part plus equal to is x dot I. Okay, so I added x to self. Is going to be changing the number. I mean, please note that is going to be changing the number. So this is basically whatever I have. I'm just adding x. I can multiply as well. So self dot r is real minus imaginary. Imaginary is real imaginary plus imaginary real. Okay, so you know this definition. And so these are the 3 functions which I wrote. Now let's see how you call this function. I call this class. Or create the object with this class. So this is I ran it. So I'm just going to write it. I can run it as well, maybe at the end. So run complex dot. Well, these are name of the file. Okay, so I like to use IPython. Many of you use Jupyter Notebook. It's okay, but I do it on my own computer. Okay, so once I do this, my class is defined. Class definition is in the RAM, in the memory. So I create an object A. So this is object A. So it's a of class complex. Its arguments are 1, 1. That means the real part is 1 and the imaginary part is 1. Now a dot print number, no argument because it was self in that there. Print it is 1 plus 1j. I create another object x of complex class 2, 3. So this is 2 plus 3j. A dot add x. So I add x to A. So what should be A now? So 2 plus 1 is 3 and 3 plus 1 is 4. Okay. So after this, A should be 3 plus 4j. Okay. And indeed, A dot print number is 3 plus 4j. Okay. If I just say A, it's not going to give me anything. It just says it's a object of complex, a type comp. Well, it's a object of complex class. You have to use, you have to use the function print. So is that clear? People can ask me questions in this. So in Python, the list is a object. So you create a list, x equal to 1, 2, 3. Then you say x dot append, right? 4. So what happens? After this, X becomes 1, 2, 3, 4. So append is a function associated with the list. So this is a creation of an object X. Of course, we don't write the list here. Some of it is done inside the Python interpreter, but this creates an object of list. Okay. So in fact, Python, everything is object, including functions. Okay. Now this tells you that there's some object thing going on, X dot append. You see a dot means objects. Okay. Now let's create slightly more complex objects, a complex class. So I create a complex class called DOB, date of birth. So it has 3 fields: year, month, and date, of course. So self.year is here, self.month is here, self.date is date. For testing, I put an empty thing. That means there's nothing in it. Okay. I can instantiate it. So I can say D equal to DOB, bracket 3 fields: year, month, and date. So year could be 2001, 1. Okay. So D is a object of class DOB. So D dot year will give you 2000. Okay. In fact, it will print 2000. Now create a more complex thing called member. Okay. A human being. Okay. Now who has a name as well, along with the date of birth. So member class, but within a class, I define this class. So this class I can put inside as well. So there's a definition within a definition. Now I instantiate this member class. So I need to use init, init. So init has name, year, month, and name as well. Okay. So basically, this is a person. So name. So when I need year, then I have self.dob.year. So this is dob inside the member. Huh? So this inside the member. So you can see that this is inside. So if I were to say P is a member, name, you're going to put a name, Rahul, and date of birth. Okay, the 3 things. So then if I want year of this, P dot dob dot year. So this, if I print this, I'll get the year of the person. Date of birth, year of the birth of the person, P. Okay, whose name is Rahul. P is an object. P has a name inside. Okay, P is an object. So you may know that file is an object. File name is a field of the file object. File data is a data of the field object, a file object. Okay, so these are objects. Now let's make it slightly more complex. So this is the last theory part. Okay, now after that we'll just go to practice. So this is a very important thing, inheritance, which I'm not using it too much for my design of CFD codes. But this we used it earlier. Okay, but right now we'll not. I don't want to use it. We keep it simple. So inherit means you inherit. No, I mean a child inherits parents' properties. Okay. So parent class or base class is called base class as well. So child class inherits the properties of the parent class. Okay, this is called inheritance. Okay. Now how do you implement it? So basically, we can create a more complex class. Okay, a child gets a property of the parent plus also builds his or her own property. Okay, so it gets added up in that sense. So the definitions are like this. So remember, I already defined member class before. So member had name and date of birth, but a student is a new class, is a child class. Okay, so it has property of the parent, which is member, And also it has another field called roll number. So student has a roll number. Okay, so this is roll number. So a student, I could have called instead of member a person as well. Okay, so in fact, I think of school. School has members. Some are students, some are teachers. And so we create a different class for students and different class for teachers. So a teacher also has a roll number, but not that roll number. It is a different roll number. Like in Kanpur, we have PF number. Okay. But well, students don't earn salary right now. I mean, if you're a company, then of course you can earn your salary, which students are now encouraged to. But well, faculty, they have salary. Okay, so salary class, I'm not putting it here, no salary thing, but it's a field with teachers. Okay, so you can see that we do not want to put unnecessary fields with the object. We should put fields which are necessary for that object, and you should associate with that object. Also, functions should be associated with that object. So the functions related with teachers, which are not related with students. No, for example, give grade to a class. So that will be a function of a teacher. But student will earn grade. Okay, so or take class. So we'll have functions here, separate functions and separate functions here. Some functions may be common. Okay, like sports activity, both may be doing it. No, so remember, there are some functions which are common among both, but there are functions which are different. So we need to create that difference, and that is what is done. Okay, now instantiation is interesting. So please see that so student definition, I'm doing it here. So these are the fields, no? Name, year, and roll number. So there are several ways to do it. I can say member in it. So member is where the instantiation requires these 4 fields. And now roll number is a unique thing, no, of a student. So self.roll number is roll number. Here for teacher, there is a salary field, and self.salary is salary. Okay, so these are 2 classes declarations. In fact, I have only initializations. I didn't write any function, but this is just to test. So student 2, I can say student. So the name of the student is Sahil, year, month, date, and these are roll number 100. Okay, you could also do for teacher. Okay, so teacher 1 equal to teacher. Don't use the same. Teacher is a class word. No? So normally it's a good idea to put capital for the class definitions. Okay, and variable names typically start with small letters. Okay. And here it could be the whole year, birth, and then salary. Okay, so some number overlap. So there are 2 objects I created. These are the objects. And these are definitions. Okay. Until you instantiate it, you're not created an object. You need to instantiate it. You need to create these objects. Then only you can call functions or manipulate the objects. Okay. Now, any questions so far? I mean, these are very preliminary discussion of objects. Any questions on them? Okay, is it clear to everyone, or is it like you got it, but you don't fully know whether you got it? So let's see. So you got it completely 2, somewhat 1, and nothing is 0. So let's see. 2 is full, got 210. Please type in chat box. So people with 1, what didn't you understand? Can you just speak up? No, I mean, I'd like to clarify. It is not an easy concept. Object oriented, I mean, is a very important step in computer programming, and Of course, you'll come with experience, and you can take these examples, play around with it. I'm not giving you homework. Like Ramdas, what is the thing which is not clear to you? Can you tell me?
So nothing in particular. I'll just go over this in the tutorial links that you had mentioned.
Right. Okay.
I just need some experience.
Yeah, I know. It's that's why I said it's. Vimal, you have something which is like, what is hazy?
One thing I thought about object-oriented programming was sometimes in particular about Python. In Python, we don't have type safety. That's why many a times while doing a program, it had bugged me a lot.
Okay,
That was
so,
something I was thinking.
okay, so you can take. I'll put all the codes in the Dropbox, and you play around with it. All the codes work. Of course, they're very rudimentary codes. Huh? I mean, so you can just apply them. Okay. Now let's now go to the real how you should design Schrodinger equation. Okay. Well, this is my take. Of course, this is not only one possibility. There are many possibilities. So this is what how I thought could give a cleaner code. Okay. So, but you can try yourself. But let me just. So these are our equation. Okay, Gauss-Peterbilt equation. So we have function psi, wave function psi. We have potential nonlinear term. You know, so these are right hand side, and there's a derivative as well. Okay, it could be 1D, 2D, 3D. Okay. Now I want to code it. Of course, you can create an array psi. You can do all these derivative operations, and you can write the code. Okay. But once you write the code, typically, if you want to use it for 2D and as well as 3D, it is likely that you're going to write another code. Okay. So that's where you'll have 3 codes, and then you have to write 3 times, you have to debug it 3 times. It's a headache. So try to make one code, okay, for all 1D, 2D, 3D. Okay, so let's see how we can try it. Okay, and I've not written it. Okay, so let's say I don't have 2D code myself. My group lab students have done it, but I would like. I mean, if I were to write a code, I will design it this way. So let me just tell you the thing. So this is only a design. Okay, so this is a box where you need to. This is abstraction. I mean, it's more than algorithm, but it's a design. So I'll create a class called wave function. Okay, so this is more than just creating an array. Okay, so I'll first think of what are things which are required for solving my equation. So I'll just try to abstract that into a class. So initialization. So this is a finite difference code. Okay, so finite difference, I'm working in real space. So I give just think of 1D. So you give me the initial condition at the grid points, and I just initialize it to self.f, right? So this is assigning it to f. So I need to initialize. No, I mean when I time step the t equal to 0, initialization. Now I need operators, derivative operators, d. So I say, well, I want any derivatives. So dn is nothing but nabla to the power n of psi. It could be in 1D, 2D, 3D, and n can also be general. Okay, so this is a very general function I want to make. Okay. Now, of course, this it could be one function, or you can call more functions, but it's good idea to just make this function. If I give a n, it will give me an output. In fact, instead of writing it elsewhere, I may create a self dot diffusion term. Diffusion term is an array. Right now I create empty and I'll fill it up with arrays. Okay, so depends. I mean, these are the things which you need to take this decision. You don't want to write it, create arrays and write it every time. You create arrays for the diffusion term, that grabs this thing. And these are empty array. And in fact, I have written codes for 1D that I also share. So we can create an array and you write on that array. Okay. So it's not that you left it hanging. This should not return an array. And then, you have to figure out where to write. I'll probably show you. Okay. I have time and I will show you a 1D array where I created this thing and it writes on that array. Okay. So it not only F, but it can have self.diffusion term, self.nonlinear term, all that you can create inside, and you can create the arrays. Okay, right now empty, but you create array next. Well, there are functions to do that. Now we also need psi power n. No, so remember I have mod psi square psi in nonlinear Schrodinger equation. Of course, you don't want to make it too general so that you're just spending all the time writing this dm. So for this class, I would say that just return Laplacian. Okay, so just return Laplacian. Sometimes we are too ambitious and it just takes too much time to write these functions. But just create right now, instead of dn, I would say that just create Laplacian. Okay, better to get it for 1D, 2D, 3D in one function. It's possible. In Python, it can be done. So psi power n, I could say that you compute this here. And it will put in nlin or something. Okay, I don't know. I mean, you have to figure out where to put. Now, this is F cross V is the potential. So this is V times psi, no? So we have V times psi. So this will be done here. So these are the functions. Given psi, I can, or given, of course, V will be an argument. Here V is the argument. Here N, this is an argument here. Okay, so you have to decide. I mean, I'm just right now, I made some crude design, which will become refined over time. So this is my class definition, which has some data structures like F and nlin and diff and all. I would like to have it inside. And now after that, I define some functions on top of it. So time advance Euler. Okay. So this will time advance, given initial condition, it will go all the way up to T final. Okay. Or you can time advance one step, but it's going to take the argument. F is the wave function. So wave function class. So I say, well, this is the argument. No? So F will be the name of the class. Object. F is the object. Huh? So when why do I do it? Well, inside that I can say F dot F. So this will be the calling that array will be incremented. So I want to multiply this by number 2. So F dot F. So this will be multiplying by 2. Well, I basically need F dot F plus dt times RHS. So F dot, if there's RHS variable inside RHS. So this will be an Euler time step. Okay. So you understand what I'm doing? So there'll be, I should also define self dot RHS. So this will also an array, and that is the right hand side of the Schrodinger equation. So this is an abstraction. So it will be nice that given my psi, I just ask this function to advance it till the end using Euler method. Of course, they need something like dt and so on. No? I mean, it requires t final, dt, all that is required. And I did something for 1D, but again, I said this is one of the designs. You can do it better. Okay. Now, once I have these functions, then I can write my main function. So this initialization. So first you write F0. So F0 could be sine function. No? So first you make a grid like this. X is lin space, something that the lin space, then sine of X. So F0 will be an array. Then F equal to wave number F0. So this will instantiate my object F. This is like psi. Okay, if you want to call it psi, feel free to call it psi. So I call it f because I don't need to write psi, so we have to write like that. So I just wrote f. Now after that, I need to time advance it. So then I can say time. So if I want to do with Euler, time advance Euler f. You put like that. So you're just going to time advance, and then you can write it on a file, your data, or print it, what you would like. Okay. So this is the basic design for FD solver with objects. It's cleaner. I mean, I could basically put my thoughts in one page, and then each thing you can expand. Okay. So let's look at. So this is if I want to solve this thing in a spectral method. So this is using Fourier transforms. So first, this file has all the Fourier transforms related functions. I call it myFFT.py. Okay, so this is myFFT.py. And this is part of my real function I wrote. So this the parameter has all these parameters, like I need the grid size, this nx, nz. So all that is stored inside para. So Python is very nice that you can import, boom, you can get that all things sitting in para. So para.nx will give me this thing. So I don't want to write everything in one file and get confused. So parameters. So normally what we want is, if some user does not want to look at my code and figure out how it is being solved, just interested in putting the parameters and run it, great. You look at the parameter file, change the file, and for your needs, and run the code. Okay, and get the output. So that is why we want this parameter file to be separated out. Okay, so we have forward transform. Okay, this is 2 lines, So given array A, so this is the argument. I divide, my definition is a bit different than FFT definition, standard FFT definition. We divide by n and return AK. Inverse transform, we also give the wave numbers, k we need, k square. So I just define them for my need. Derivative is, remember, so in Fourier transform is ik times, so this ik ak. So this is what it is, k mesh. So we create a mesh. So this mesh can be 2D. Okay, so k mesh is created, k mesh is right now, I mesh create. K mesh is created somewhere, okay, it's outside. Okay, all right. So now once I have my FFT all set, then I can write the class. Now this is my spectral code, okay? The design is very similar to finite difference, but we need these derivatives or Fourier transforms, okay? So we basically work with wave number space. So I have 2 arrays, Fk and F. So Fk means it's in Fourier space. K is Fourier, and self.f is in real space. Okay, so my initial condition, I want to read in Fourier space. Okay, that's my desire. Okay, so I just say Fk0, and I have my F empty. When I do inverse transform, I would like to get from. So once I do the transform, I want to save it in F. I don't want to be floating around in some temp arrays and so on. Okay, we don't want that. So dn is that idea of derivative, grad n, okay, psi, or grad nf. So this will be that. So it's very similar design. F power n, like it will compute the mod psi square psi, or anything. Okay, it could be psi 4 to psi, and this is product of v with psi, v psi. Compute RHS, so that will be the whole thing minus Laplacian psi plus V psi plus mod psi square psi. Okay, so this will be the RHS. And then time advance Euler. We need to fill up all this. Huh? So these are the functions I make first. And after that, I did the main. So compute fk0. Okay, then instantiate it. So this f is now f is my name of the object. It is not same as that. Okay, and I should really call it something else because it's very confusing sometimes to this f is the same f. So maybe I should call it psi. And then time loop. So psi will be time looped for T final. So I think I will stop here. We will not go to hydro, and I think you need some time to think about it. Maybe I'll just show you the code just for completeness.